Okay, so now we're going to be going through chapter 4 of Colin McClarty's Elementary Categories, Elementary Toposes. So this is all about, or mostly about, subobjects and pullbacks. So a monic from S to A monic I, is also called a subobject of A or a part of A. And basically it represents, well, a part of A, okay? So you see in this example in set, a monic basically corresponds to an injective function, and we can see it sort of selecting a subset of A. And that's the sort of basic idea, but we sort of describe all this going on in the beautiful language of category theory, where all our results apply to innumerable different examples. So given a monic I from S to A, we have this nice notation. So given an arrow X from T to A, we say that X is a member of I, written X in I, when there exists a H such that X is equal to IH. So we have this kind of triangle commutes. And we see in this example, basically in set, what this sort of notation means. It really means, in set at least, that this function X is taking all its values in the kind of subset which I sweeps out. And this H here kind of does what X does, but it sort of preloads the elements into this subset ready to be injected with I, okay? But anyway, just take this as a definition. So it's an important definition. For a monic I, X is in I when there exists a H such that X is equal to IH. Personally, I would use this in notation even when I is not monic, but in these sort of videos, we usually use this notation when I is monic. Notice that this is different for generalized element notation because we're missing a subscript here. Okay, so also notice that when we do have the X is in I and I is monic, like in this video, whenever we write X in I, we assume that I is monic. Well, that means that this H, this kind of thing that we precompose with, is actually unique because we need that X is equal to IH. Well, if it was another H dash, we're similar. So we had IH is X is IH dash. Well, since I is monic, that implies H equals H dash. Now, a few more properties of monics. One is that the composition of monics is monic. So suppose we have a monic I from A to B and a monic J from B to C. Well, then J after I is monic. We see that since J after I after X equals J after I after Y implies, since J is monic, that implies that IX is IY. And since I is monic, that implies X equals Y. Another result about composition and monics is that if we have an S from A to B and a G from B to C, and we have that G after S is monic, then that implies S is monic. So we can see this since SX equals SY implies GSX equals GSY implies X equals Y. Okay. Now, let's consider two monics, I and J, that are both going into C, or, using our new terminology, we could say let's consider subobjects I and J of C. Okay, well, if we have that there's if we have that I is in J, so that means there exists an S such that I is equal to JS. And also if we have that J is in I, so that means there exists a T such that J is equal to IT. So I've just said that here in more explicit notation. Well, that implies that T is actually the inverse of S, so that this S and T are actually isomorphisms. So how can we see that? Well, just using these equations here, I is equal to JS and J is equal to IT, we get that I is equal to JS equals ITS, and then since I is monic, that means the identity is equal to TS. Similarly, J is equal to IT equals JST, since J is monic, identity equals ST. So that shows S and T are isomorphisms. Now, when we have the a monic, we have this kind of situation, or at least part of it. So we have that when a subobject I of C is in a subobject J of C, we'll sometimes write I subset symbol J, and we say that I is included in J. Okay, I mean, that's really, we can just write in instead, and I often do that. I think this notation is a bit redundant, but you know, it's nice to sort of connect with the set theory notation, I suppose. Anyway, and then also notice in this case, there's obviously got to be an S such that I is equal to JS, and that S has to be monic because we know that JS is monic, and then using this theorem 4.1 here, that implies that S is monic. Okay, and that makes sense because we've got kind of subsets and stuff. Another bit of notation, when I is included in J and J is included in I, we write I is equivalent to J using these three kind of equals lines. And in that case, the domain of I is going to be isomorphic to the domain of J. That's just a consequence of theorem 4.2. Okay, next result then. Theorem 4.3, when we have two subobjects, I and J of C, we've got that I is included in J if and only if we have this statement holding on generalized elements. And it basically says, whenever we have for any T, we have that for any X element of C, we have that X is in I implies X is in J. So this is lovely, actually. This is really sort of taking this statement about monics and turning it into this statement about generalized elements, and it's an equivalent way to say it. Okay, so we often go to sort of this generalized element notation when we can, because often when we're talking about stuff like this, we're talking about kind of abstracted things from set theory, and when we put them in generalized element notation, we can basically often just apply the same kind of set theory based reasoning to them. Anyway, how can we see the proof of theorem 4.3? Well, why do we know that I is included in J implies this statement at the bottom? Well, suppose I is included in J, and suppose that X is a T element of C. Well, if we have that X is in I, that means there exists a H such that X is equal to IH, and then we have that J is in, then we have that I is in J, so there exists an S such that I is equal to JS. So X is equal to IH, I is equal to JS, so X is equal to JSH, so X is in J. So we've shown this statement holds when I is included in J. Now let's suppose this statement holds. So whenever we have a T element X of C, we have X is in I implies X is in J. Well, we do a commonly used trick. We look at how this statement works when x is equal to I. Well, I is in I because we have this identity arrow to sort of form the triangle. And so since we're assuming this, we have that I is in J, and that's just a fancy way of saying I is included in J. So that finishes the proof. A corollary of this is what it means for I to be equivalent to J, and it basically just means I and J have the same members, okay? So we have X is in I if and only if X is in J. So basically I is equivalent to J, like in terms of set theory. For example, think about this. We could select this subset by a subobject like this. True and false, or we could select it with this kind of monic here from 1 and 2. So the domains of those monics are obviously isomorphic, as we've proved in general, not just for sets, but also, you know, stuff's going to be in you know, where these arrows point to for one monic if and only if it's in the other one. So there we go. We can also get a we can also think more about equalizers and how, because we know equalizers are monic. So given that E is an equalizer of F and G, suppose that I is a subobject of A, well, that's going to be an equalizer of F and G if and only if I is equivalent to J. Okay, so I mean, if we think about in sets again, an equalizer is just going to be the set of all elements from A, such that the set of all elements X in A, such that F of Fx equals Gx, and you know, we can describe that if I sweeps out those same elements that monic does, same as E, then of course that's going to be an equalizer of it too. This IFF means if and only if, okay? I could also write left statement implies right statement, right statement implies left statement. Okay, another theorem then. This gives us very nice characterization of equalizers in terms of generalized elements. So this holds for a monic little e from object capital E to A, and what it says is that E is going to be an equalizer of these parallel arrows F and G if and only if we have this statement holding that X is in E if and only if Fx equals Gx for any arrow X into A. Okay, so let's prove this. So I'll call that statement 1 that E is an equalizer, and this statement 2 at the bottom here in blue. So suppose 1 is an equalizer. Now, if we have Fx equals Gx, that implies there exists a H such that X is equal to EH by the property of the equalizer, and that implies that X is in E. So we've shown that when 1 holds, we have this statement on the right implies a statement on the left. Now let's do the converse. Suppose X is in E. Well, then there exists a H such that X is in EH. That's just what X in E means. And then that implies that Fx equals FEH equals GEH, since F equals G, and this is equal to Fy. So we have Fx is Fy. So we've shown that the statement on the left-hand side implies the statement on the right. So we've shown that 2 holds true in this case. So we've shown that statement 1 implies statement 2. Now let's go the other way. So suppose statement 2, and consider what happens firstly when x is equal to e. So when x is equal to e, we have e in e, and since we're assuming 2, that implies Fe equals Ge. So we've got that E equalizes F and G. Now suppose that this arrow x from T to A also equalizes F and G, so Fx equals Gx. Well then, since we're assuming 2, that means that x is in E, and since E is monic, that means that implies that there exists a unique H such that x is equal to EH, which is the property of the equalizer. Necessary and sufficient, so we have 1. So we've proved that theorem, and basically notice that these subobjects and this equivalence thing with the triple arrows is an equivalence relation, and subobjects are basically just defined up to equivalence. So a lot of authors speak about subobjects as equivalence classes of monics, using this triple horizontal line equivalence relation. But usually we're talking about particular monics, but often it doesn't matter. You can just talk about them up to this sort of isomorphism. I mean, usually when you're working in things like set and presheaves and things like that, you can just pick an inclusion function as a kind of canonical representation of one of these equivalence classes of monics, as a certain sort of subobject. So for example, in sets, if you have A, B, and C, there are many monics which go like this from some sets, but a nice one to pick is the one that just sends A and B to that. Okay. Now, next thing we want to define is a pullback. So a pullback. Okay, so when we have a couple of arrows F and G, which are both coming into an object C, we call that a corner of arrows. So here's a corner of arrows. It's an arrow F from A to C and an arrow G from B to C. Now, pullback of that consists of an object that we might call A times over CB, with projections P1 to A and P2 to B. And it has to be a pullback. Firstly, it has to make this kind of black square commute. So we have to have F after P1 is G after P2. And secondly, it has to have the property that for any T with arrows H into A and K into B, such that FH is GK, there has to exist a unique a unique U from T to A times over CB, which basically makes this diagram commute. So we have P2 after U is H, P1 after U is H, and P2 after U is K. All right. So that's what a pullback is. Basically, we can also think of pullbacks in terms of limits. So we could say it's the limit of this kind of corner. I mean, if you think about it in terms of limits, these kind of projections, P1 and P2, are part of a sort of natural transformation, and there'll also be an arrow going into C in that natural transformation, but it's a similar story to what we had with the equalizer, in the sense that that third arrow that goes to the bottom right corner is kind of redundant because all of its information is implied by the other arrows. So that's why we just think about these pullbacks as an arrow into A and an arrow into B. And so anyway, since these pullbacks are limits, we have they're basically defined up to isomorphism. Let me just restate the definitions. Pullbacks are absolutely, they're very, very important. I mean, basically, if you have pullbacks for every corner, and you have terminal objects, then you have all finite limits. There's a very strong property saying that pullbacks always exist. So let me just restate the definition again. And that's that we want this object A times over CB with arrows P1 into A and P2 into B, such that F P1 is G P2, and also for any object T with an arrow H into A and an arrow K into B, such that F H is G K. We have that there exists a unique arrow U from T to A times over CB, which we may also write sometimes as H comma K using the sort of product terminology, but this has to be unique such that P1 after U is H and P2 after U is K. All right. So we have our usual kind of pullbacks are defined up to isomorphism theorems. The first one, given two pullbacks, this one with projections P1 and P2, and this one with maybe a different object Q and projections Q1 and Q2, there exists a unique U from Q to the object of the first pullback, such that Q1 is P1U and Q2 is P2U, and that U is going to be an isomorphism from A times over CB, well, from Q to A times over CB. All right, so that's the first result. Again, this is just analogous to what we had with products. The second result is that if A times over CB is a pullback with projections P1 into A and P2 into B, and Q is an isomorphism, sorry, I is an isomorphism from Q to A times over CB, then Q with projections P1 after I and P2 after I is also going to be a pullback of our corner of arrows. Again, like with products, we have component-wise equality implies equality. So if we have two arrows from T to A times over CB, say H comma K and H dash comma K dash, then if H equals H dash and K equals K dash, then those two arrows are equal. Let's also think about how we can talk about pullbacks in terms of generalized elements. So a nice property that they have is that when we have an arrow x comma y from T to A times over CB, then we've got x is a T element of A and y is a T element of B, and fx equals gy. Okay, so that kind of suggests that we can write a pullback as a kind of combination of a product and an equalizer, and we're going to see that that is indeed so.